exhibiting thermal differences by virtue of water circulation. And the example that I mentioned very early on in the semester, when we were earlier on in the semester, when we were talking about denudation and uplift and erosion and all that kind of stuff, was changes in elevation and disposition of orogenic belts. And the example that we talked about were the Himalayas, in which I pointed out that the Himalayan front ranges of the Himalayas today form such an impressive barrier to atmospheric circulation that you have this major climatic condition in the subcontinent of India known as the monsoon period. And the monsoon is essentially tied to the air circulation patterns that essentially the warm, moist air of the Indian Ocean moving north over India hits that almost vertical wall of the front of the Himalayas, forcing the moist, warm air upwards and causing it to drop its moisture and giving you the torrential rain of the monsoon season. And clearly that has a major influence on various of the geologic processes that we've been talking about, weathering, erosion, those kinds of things. So not only is the disposition of continents and ocean basins and the geometry of the ocean basins important because it influences oceanic circulation. Imagine what would happen in the world today if we were to remove the Isthmus of Panama. In other words, if we were to open a link between the Atlantic, Caribbean, and the Pacific. There would be significant changes in ocean circulation patterns if that were to occur, and that would have a significant effect on weather in general and climate in particular. So ocean circulation is important, but atmospheric circulation can also be influenced by changes in the nature of the Earth's surface, which is what the kind of the title of the slide addresses. So the third kind of explanation for climate change is atmospheric composition, and obviously we are here talking about greenhouse gases. The greenhouse climatic effect, was first recognized in the late 19th century, so it's not a kind of a recent concept that's been developed or recognized. We've known about it for well over 100 years at this point. I've got two greenhouse gases listed here, carbon dioxide and water vapor. I could, of course, add that there are other greenhouse gases, the most notable of which I don't have listed is methane. And methane, it turns out, is ironically is a more effective greenhouse gas than carbon dioxide, but it has a much shorter residence time in the atmosphere. Carbon dioxide has a fairly long residence time. It's hard to calculate, but meteorologists will talk about 100 to 200 years, that sort of thing. So, and that's important, obviously, because people talk about reducing the amount of carbon dioxide we put into the atmosphere. That's probably true. But what we are putting into the atmosphere today is going to be there for quite a while. Methane cycles through a lot quicker, apparently. But when it's there, it's a very effective greenhouse gas. And I noticed the other day there was a report in the paper that the Japanese had made the first successful exploitation of these things called clathrates or hydrates. These are these methane deposits, frozen methane deposits that you find in the sediments off North America, off Japan, and off many other continents. There's a huge reservoir of methane apparently frozen in the sediments of the world's oceans. And one of the great fears of trying to exploit that resource is you could start a runaway process where you start to produce the methane, and then it would be kind of a self-sustaining activity. Whether that will occur or not, I don't know, but if it does, it would be pretty catastrophic in terms of changing the composition of the atmosphere. So we'll kind of stick to a discussion on these two gases primarily to see how it is that they influence climate. Well, because the argument is, and it's true of any greenhouse gas, but obviously the same for carbon dioxide, if you have a rise in CO2 in the atmosphere, that will cause, because of the greenhouse effect, the temperature of the atmosphere becoming somewhat warmer. When that occurs, the atmosphere is capable of holding more water vapor in the atmosphere, and water vapor itself is a greenhouse gas, so it becomes a kind of almost like a self-exciting system when that happens. So, and if you look at some numbers that people like to throw around, if you take the present day concentration of carbon dioxide in the atmosphere, which I think is at its highest level for 800,000 years was the number I was just looking at, but it's pretty high. If you were to cut that in half somehow, it would cause the worldwide average temperature to drop by about 4 degrees Celsius. On the other side of the coin, which is more likely than the first point that I made there, if we were to double the CO2 concentration in the atmosphere, you would increase average temperatures by about 8 or 9 degrees Celsius. And here, remember, we are talking about average temperatures. I mean, so you figure 8 degrees, it's 80 degrees out, what's the difference? 80, 88 is no big deal, it's just a little bit warmer. But these are average temperatures. So that gets to be a real major issue, obviously, in terms of the effect on climate. So the obvious question then is, if these greenhouse gases are players in the game of modifying and altering our climate, what changes CO2 concentrations in the atmosphere? Well, today, of course, you only have to look out the window and you can see why, because you have cars burning fossil fuel, or any fossil fuel that you burn, gas, oil, coal, or whatever, you're going to release what I like to call paleo-solar energy into the atmosphere. But as I pointed out, the dinosaurs didn't have SUVs, so there must be other reasons why the CO2 concentration changes. And you get into a very interesting debate at this point, because there are arguably two sources of carbon in the carbon dioxide system, one related to the organic side of the equation, and the other one on the inorganic side of the equation. Some people believe that the organic carbon dioxide cycle is essentially balanced, roughly balanced anyway. And so plants are effective in fixing carbon into biomass, obviously, through the process of photosynthesis. And so they're, on the one hand, they're sucking carbon out of the system. But of course, when the plant dies and decomposes, you put the CO2 and the associated carbon, obviously, back into the system. And the point that I was making earlier about black shales, about coal, about oil, that represents undecomposed carbon, as it were, that was generated in the past. That those accumulations of material didn't undergo the oxidation process to destroy that material. And by virtue of burning that stuff today, we are doing what may have happened or could have happened millions of years ago, but now it's being generated today. If we accept that middle bullet there as being approximately correct, and I don't know if it is or it isn't, but that's an argument put forward by some people, if that's correct, then the bulk of the CO2 variation that you might see historically that influences climate it may well be related to the inorganic